What will happen to the planets when the sun expands? Why is Venus's atmosphere so thick? And does everything produce Hawking radiation? All this and more in this week's question show. Welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down and I will gather them up and I'll answer them here. All right, let's get into the questions. Metin some Turk 2552. How do we know that the orbits of the planets in the solar system will remain the same as the sun expands? So as we know, the sun is a main sequence star and it is about halfway through its lifetime. And in several billion years from now, the sun is going to run out of usable hydrogen in its core. And then it's going to try to switch to another kind of fuel like helium. And as this happens, it actually heats up the core of the sun and it causes its outer layers to expand outward. And then it will shed a bunch of material. It's going to cool back down and then it's going to expand again, cool back down. And each time it's going to lose more and more of its mass. And eventually the sun, once it's gone through this entire sequence, it's run out of usable fuel in the core, it will just be the leftover core of the sun. And that will end up being about 46% of the mass of the sun. Now, during that process, as the sun expands out into a red giant, it is going to enclose the orbits of the inner planets. It's definitely going to enclose Mercury and Venus, and there's some sort of arguments back and forth about whether or not it's actually going to consume Earth. And the reason there is this question is because we don't know how much of the mass the sun is going to lose. And the orbits of the planets are dependent on the mass of the sun. If the sun loses mass, then the planets will actually change where they're orbiting. They'll move, I guess, closer in as the sun is losing mass. And so you're going to get that expansion of the sun gobble up potentially Earth. So we know that the orbits of the planets won't remain the same. They will shift as the sun changes in mass. But another interesting thing is that the sun is actually losing mass all the time. It's losing about 6 million tons a second. And that's due to fusion in the core, as well as the solar wind that's coming off of the sun. But in fact, that amount is pretty negligible to the mass loss compared to when the sun goes into that red giant phase. So what feels like stability today is actually just one time in the main sequence phase of the sun. And then later on, everything is going to change as the sun goes into that red giant phase. I'm sure you noticed the Star Trek planet name that appeared above my shoulder on the first question. Of course you did. You're very observant. That is a way for you to vote, for you to tell us what you thought was the best question of the episode. So we're going to have a different Star Trek planet name above my shoulder for each question throughout the entire episode. And then we'll put links to all of them as part of the show notes. And we'll have the, in the timeline. And so you can see what all the planet names are. And then at the very end, after you finish watching the entire episode, go ahead and put in that question. So, I forgot to say though, so the winner for last week's episode was from Keturi. Would it be possible to use the moon's huge temperature difference as a power source? And we talked a bit about using stored solar energy in the regolith, similar to some of the sand batteries that are being proposed here on Earth. All right, so don't forget to vote. JWST. How interesting is the information of dust particle size and speed distribution along the solar system? My intuition is that this information is absolutely precious, but it seems that it's not that interesting. Is there no plans to make probes that can record it? Not even the concept of probes to perform that task. Why not? What makes you think that this has not been implemented in a probe? So NASA's New Horizons spacecraft, which has done the close-up images of Pluto and Charon, then went on to see Kuiper Belt object Arrokoth, it was equipped with a dust measurement device. And so as it was passing through the solar system, it was measuring the amount of dust. It's got this, it's essentially able to measure the impacts of dust onto the spacecraft as it's moving forward through space. And one of the really interesting scientific measurements that just came out a couple of months ago was that New Horizons is still seeing a lot more dust, even though it's largely through what should be most of the Kuiper Belt, it's still seeing a lot of particles farther and farther out from the sun. And so this means that maybe the Kuiper belt actually extends a lot farther than astronomers had originally thought, or maybe it leads into a second Kuiper belt that's even farther away. So dust is incredibly important to measure in the solar system. There are spacecraft that are able to do it, and there are more planned. So there's an entirely new mission that's in the works called the Interstellar probe. And the plan for this is that it will fly out beyond the distance that New Horizons, the Voyagers, Pioneers, and really get out into interstellar space, beyond the heliosphere of the sun and into interstellar heliosphere, the one from all the other stars in the Milky Way, and get a real sense of how much does the sun's solar wind, as it creates this heliosphere, how much is this protecting us from the particles that are coming from the rest of the stars in the galaxy. Now, one of the other things that New Horizons did, which is kind of related to the dust, is that we know there is this dust that is embedded into the solar system. You can take pictures of it when you're on the surface of the Earth. It's called zodiacal dust. And it is this dust that is in the sky along the plane of the ecliptic. So where all of the planets are in the sky, there's also this dust trail that's in between it. It's easiest to see sort of shortly after sunset, just before sunrise. You can see this zodiacal dust. And in fact, recently astronomers have discovered that this dust is probably linked to Mars. This dust is probably coming from Mars and has spread out into the sort of plane of the ecliptic, and is this dust that obscures part of our view. And one of the questions that astronomers recently wanted to know is how much is this dust obscuring our view of the cosmos? I mean, it's kind of the equivalent to having light pollution or atmospheric dust here on the Earth. If you're down at the bottom of the atmosphere with a telescope and you're looking out through space, and you're looking through the atmosphere, we know that it's much better to be out in space with a space telescope. But the question is it better to be close in to the solar system, or is it better to be far out in the solar system? And so one of the things that New Horizons did was it just measured the darkness of space itself. And it was able to determine that, in fact, there is a lot of dust that is causing a slight hampering to the astronomical imaging that's done by telescopes that are in the inner solar system. So we have all these giant space telescopes around Earth, the L2 Lagrange point, and that's just because it's convenient. But the best place to put a space telescope would actually be way out beyond the orbit of Pluto, beyond most of the dust. You get the clearest, darkest view of the cosmos. But it would be a total pain to send a telescope all the way out there, which is why you keep them relatively close. Wink. How come Venus's atmosphere didn't get stripped away by the sun in the same way that Mercury's did? And how come Venus's atmosphere remained so thick? This is actually a completely ongoing mystery that astronomers aren't entirely sure. So let's talk about a bunch of the factors that have been considered in the past. So the first thing is that obviously Earth and Venus are much more massive than Mars. And so one of the thoughts is that because Mars has a lot less gravity, then it has been losing a lot more of its atmosphere compared to the other larger planets. And that's partly true, but it doesn't sort of explain a lot of it. So one big defense that people think is that the Earth has a global magnetosphere, which protects us from the impact of the solar wind, while both Mars and Venus don't have global magnetospheres, and so they have no protection. But in fact, the amount of atmospheric loss from the lack of a magnetosphere isn't that big. So there was a paper that came out just a couple of years ago where they calculated how much water would have been blasted away off of Venus over the course of 3.9 billion years. Like if it had water for that entire duration. And according to the researcher, it's about 0.02 to 0.6 meters of depth, of water depth across the entire planet. And so when you think about how deep Earth's oceans are, kilometers deep, and if you just like averaged all of the Earth's oceans around the entire planet, it would still be kilometers deep. And yet, if you lost just a meter to space over the course of almost 4 billion years, it's nothing. So why doesn't Venus have water. And this is like a big mystery. And one of the big reasons why NASA is sending a mission back to Venus, they've got actually 2 missions they're sending. There's the Veritas mission, which is going to help to map the surface of Venus. And then there's Da Vinci Plus, which is going to help to measure the atmosphere of Venus. And NASA did a fairly recent spacecraft called MAVEN at Mars. And one of MAVEN's jobs was to measure the water loss, the atmospheric loss that's happening from the solar wind on Mars. And they came up with sort of the same thing, which is that, yes, there is water, there is atmosphere being lost from Mars, but it's not as much as you would expect. And it doesn't explain the complete and total lack of water. And so now there are alternative explanations that maybe the water on Mars, maybe the water on Venus went inside the planet, that it sort of absorbed that water. And unlike Earth, Venus and Mars don't seem to have plate tectonics. There's no global plate tectonics that seems to recycle the surface and keep the water up on the surface. So maybe at some point the water seeped into the planet and is now out of sort of connection from the atmosphere itself. But maybe all that water is still there, or most of that water is still there. You know, I think a couple of years ago, I would have just given you a very flippant answer, like Venus doesn't have a magnetosphere, and so it wasn't able to stop the hydrogen from being blown away from the sun. And oxygen is 16 times heavier than hydrogen, and so it kept its oxygen, which bonded with carbon, and it lost its hydrogen. But then, of course, hydrogen is part of the solar wind. In fact, there's fresh hydrogen hitting Venus all the time. So anyway, so I would have given you that very flippant answer. And then Mars, you know, lacks a global magnetosphere. It's much less massive. It would easily lose its water mass. But now it really looks like the story is going to be a lot more complicated. And so more research is needed. It is an active mystery. Stefan Anderson, 7519. Very interesting to hear you explain the Unruh effect. So would that mean that everything with mass creates Unruh radiation around it? Would an immortal being ultimately evaporate just like a black hole? So 2 weeks ago, last week, I gave a fairly detailed explanation of Hawking radiation. And the important part here is that it's not this virtual particles appearing right beside the event horizon of a black hole, that actually there is a different, more complicated explanation for it. One that Hawking totally knew and should have given, but he felt like people weren't, I don't know, smart enough to handle it. And so that's how we've got this virtual particles appearing. It's caused all kinds of miscommunications and misunderstandings for decades. And you talk to particle physicists and they wince. So hopefully I'm trying to set the record straight on Hawking radiation, and go back to that other episode if you want to hear the explanation. But the question that you're asking is one that has come up. And so if it's not a black hole's event horizon that is causing this radiation, but in fact, the gradient of the mass difference as you go down the gravity well, then does that imply that all mass evaporates? And the answer is probably yes. So there was a paper that came out a couple of years ago where researchers asked this exact question. They said, well, does all mass emit Hawking radiation? That with a black hole, you've got the most gravity and especially the most gradient where you've got that event horizon. And so you're going to get the highest amount of Hawking radiation from the least massive black hole. You're going to have less Hawking radiation from a supermassive black hole. But in fact, they calculate that there would be some level of Hawking radiation coming from any mass, but that amount would be completely insignificant. And so I guess, would an immortal being ultimately evaporate like a black hole? Yeah, over an infinite amount of time, that if there was nothing else, then eventually even that immortal being would evaporate. In Captaton, why is Neptune used for naming exoplanet categories, but Uranus is not? Oh, that's a brutal question. So people who sort of follow a lot of space exoplanet news know that there is a classification of planets called sub-Neptunes or mini-Neptunes. And there's the Neptune desert. Why don't we know about a lot of exo-Neptunes? And yeah, so there is this classification of planets. Like obviously there's the size of the ice giants, size of Neptune and Uranus, which is about 50,000 kilometers in diameter. And then there are these smaller, there's like this middle ground between a super Earth that is much larger than the Earth, but then smaller than a Neptune, a sub-Neptune. But why is it Neptune? Why isn't it Uranus? So I think there's two parts to this. One is that Neptune is a little bit smaller than Uranus by a couple of thousand kilometers. And so if you're going to have smaller than Uranus, you might as well say Neptune. And so, but if you're going to say Neptune, now you can actually talk about things being smaller. But then the other part is that it's the word Uranus, right? Uranus just causes giggles by anybody who says the word, who hears the word. Your anus. See, you laughed. So I think, I'm assuming that the exoplanetary community just wanted to avoid all of the giggling and just went with sub-Neptunes. But someone from that community is going to have to clear this up for me. Sion 85, what type of propulsion do you think might be used on the first manned interstellar mission? Or is it something that we have not yet conceived of? Well, before I go into this, I've got to, at the very least, assume that we are going to follow the laws of physics as we understand it. So in other words, is it possible that someone is going to come up with a new type of physics, a warp drive, a wormhole, any of that stuff? Yes, of course. That the laws of physics as we understand them are not the laws of physics as they truly are. And so at some point, someone is going to come up with something better, and then everything I'm about to say is just meaningless. But from what we currently understand today, there really is only one viable propulsion system that would allow us to go from star to star, and that's antimatter. And antimatter isn't even really a propulsion system. It's just a method of storing energy. And so we know that if you have a antimatter particle and a matter particle and they combine, you're going to get a release of energy. Essentially, it's a pure form release of energy of E equals mc squared. And so any other propulsion system is fractionally as efficient as antimatter. And the problem is that those other propulsion systems, whether it's a fusion drive, a fission drive, even having like a laser sail to accelerate to high velocities, comes with a ton of downsides. Do you want to spend 1,000 years to travel to another star system? Do you want to spend 10,000 years? Do you want to not be able to slow down when you get to the other star system? No. So an antimatter rocket, you are essentially combining matter, antimatter, you're getting a release of energy, and then you can either just use the photons themselves that are being blasted out of the antimatter, sort of use mirrors to focus them out to come out of the back of your rocket, or you can use the matter and the antimatter to heat up some kind of propellant, hydrogen gas, maybe something you're bringing in from the universe, and then you are accelerating that out in the back thanks to the antimatter. And once you get to antimatter, then you do have the kinds of densities that are required to accelerate a spacecraft, the kind that would carry passengers on board to velocities that would carry them to other star systems within their lifetime. The problem is that antimatter is incredibly expensive to create. It costs something like $62 trillion a gram. And so the total amount of antimatter that has just been made by all of humanity is orders of magnitude less than would be required to even send the smallest possible probe, like a robotic probe, to another star system. That we need to scale up our antimatter production by many, many, many orders of magnitude. We have to figure out ways to make it cheaper. That you can imagine some future where a large percentage of the energy coming from the sun, I don't know, like 1%, is just being used to create antimatter. Then you're starting to get the kinds of energy use, storage of antimatter into a very small amount. Use that on a spacecraft. It's dense enough, gives you enough of a delta V, change of velocity, to actually be able to carry you to another star system. So really, until we get using antimatter, there isn't anything that will carry humans to other star systems. Now, you could use other systems like a laser sail, like what the Breakthrough Starshot is planning, then you would be able to send, say, a spacecraft to Alpha Centauri at 10% the speed of light, but it will have to be a spacecraft this big with a solar sail that is a kilometer across. And it's going to take it 40 years to get there. Like, that is not the right span of time for humans to actually complete the trip. So really, antimatter is the only way to go in the end. If you want to support the work we do here at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, those other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Clinton Knox, John DeBenedette, Hey Twyla, Scott J, Arvid E. Picciani, Sandra Everson Jones, Ardo, Lynn Phelps, S. Xaba, Dylan Thomas Murphy, Scott Wright, and Ed Engel. Join the club at patreon.com/universetoday. Pathogen X. What is the significance of JWST observing ethanol and other complex organic molecules around protostars? Is there yeast in space? You're exactly right that James Webb has detected a lot of really complicated organic molecules in the regions around protostars. And so for the longest time, it was thought, okay, there's just going to be the basic building blocks. You'd have hydrogen, helium, you might have carbon, and then these will come together in a stellar nebula. And then over time, you're going to get the planets forming. And then on the planets, you're going to get more complicated carbon atoms, ethanol, acetylene, methane, carbon dioxide, and eventually you'll get even more complex things like amino acids. And then from there, you'll have those first building blocks of life, and then maybe something happens to create life. But now astronomers are discovering more and more, and this has been known for a while, that not only are like these carbon atoms forming into more complicated molecules in space, but there seems to be kind of no end to this. So astronomers have detected not only, as you said, ethanol, like alcohol, in the clouds of gas and dust that lead to building a star system, but they've found acetylene and methane and just hundreds of amino acids, not just the 20 that are needed for life on Earth, but in fact, tons and tons of other amino acids. And what makes that really exciting is that it means that the raw material for life was just present before the star system even formed. That you've got all of these amino acids, all of these sugars and alcohol and all this stuff. It's just ready to go. And then as the planet forms, then it starts to rain down on the planet and build up. And then you've got the conditions where life can try to form. And so it just makes this question even more puzzling, which is, there didn't seem to be any special circumstances that happened on Earth. There's something really unique and interesting about Earth, that we had all of these amino acids and more complex molecules on our planet. It turns out in many, probably all of the protoplanetary systems that we look at, all of those raw materials are just ready to go, waiting to join the planet. One of the really interesting questions is, how do you get those amino acids and other molecules down onto the surface of the planet? That if the planet is orbiting quickly through this material, it might actually be that it has a hard time. Like, say, comets are delivering some of these complex molecules to the surface of the planet. They're smashing in at tens of kilometers per second. So it might be too fast and actually shattering and breaking those larger molecules into smaller ones. But maybe as the comets get really close and they just kind of deliver their tails into planet Earth, maybe that's going to work. Or maybe there's other ways that stuff from space can land more gently onto a newly forming planet so that you get the amino acids holding their structure. So it's, again, another part of really interesting research. And in fact, like, the work that James Webb is doing is mind-blowing, that they're able to detect the protoplanetary rings where the planets are forming gaps in the disk, and they're able to measure the amounts of water ice at different parts of these protoplanetary disks to see how maybe water is being picked up by the planet as moving around. And then, of course, the presence of all of these organic molecules in there. Like, it just makes the question of where is all of the life in the universe more complicated, because once again, Earth just doesn't seem very special. We're totally normal. Of course, you have a ton of amino acids and other complex molecules appearing on planet Earth the moment that it could, because they were present in the stellar nebula before we even got here. T-bounds. Do you think the chances of receiving an alien transmission are decreased further because they will only choose to send signals to exoplanets that they can see using the transit method? So that's an interesting question. So the transit method, this is where you measure the planets around a star because you see the planets passing directly in front of the star from your perspective. But you don't get a lot of planets that way. You really only get like less than 1% of the stars in the sky are going to be oriented in such a way that its planets are going to pass directly in front of it from your perspective. And so that cuts down the number of planets that you could potentially see down to a fraction. The planets that we can see through the transit method isn't the same as the other way around. And so in other words, maybe we can detect them, but they can't necessarily detect us, and vice versa. And so, I mean, I think it's a good start. Like one of the big questions that you always have to ask with SETI is how do you narrow down the search? Space is gigantic, and there are 100+ billion stars in the Milky Way. How do you know which ones to look at, when to look at them, which wavelengths of radio are you going to try to listen to them? And so anything you can do to filter that number down to a smaller number is a good idea. And so one of the interesting ideas is that you can calculate which planets would see us as a transiting exoplanet. And that's possible. You know, these calculations have been done, that you can figure out which of the stars out there could see us as a transiting exoplanet. And then the next thing you would say is, okay, so if we know that that star sees us as a transiting exoplanet, when would they see us transit? They would know to send a message that when we line up with that star, we should see a message coming from that star when it happens. And this idea has been proposed, and it has actually been done. Like, radio astronomers, SETI researchers have trying to time when we appear to be a transiting exoplanet to some other star, then to check that star to see if they send us a message. And obviously, you know, it hasn't worked. And there's been a lot of other ideas. Like, there's a whole field of thinking about these kinds of timing systems. So another one that I did an interview with a researcher a couple of years ago, maybe a year ago. Anyway, and so the idea is that when there's a supernova goes off, then that is a sort of single beacon that happens in the universe. And there is going to be this cone of, like, this light cone that's coming out from the supernova, where there are going to be various star systems within that light cone that are going to perceive the supernova. And when they see the supernova, then they'll be able to calculate when other stars within that light cone will also see the supernova. And they can calculate the time to say, okay, when that star sees the supernova, we're going to send a message so that it is received at exactly the same time. They will see the supernova, and they will also see a signal from us saying at this exact moment is when you both see the supernova, and you would expect our star to be able to send a message to you. Come look at our star at this exact moment. There's another idea that I really like, which is that there are a bunch of stars that are orbiting around the center of the Milky Way, the supermassive black hole that's at the heart of the Milky Way. And one of these stars is coming extremely close to the black hole, S2. I think it takes like 16 years to be able to orbit. And so it is essentially carving out it's like a clock that is happening, like a second hand that's happening at the center of the Milky Way. And so you could expect that other civilizations would notice that this star is doing this really tight orbit around the Milky Way, and then use that as a way to time their transmissions to each other to line up with this rotation of this star, because it's something that we can all do, and you can sort of dramatically drop the places to look. Let's only look in the places where they are mapped out by this, the quadrant of the sky that's being mapped out as a star is moving around the black hole. So, just this idea that you're mentioning, one is like, try to communicate with people who see us transiting, try to communicate with people who know that a supernova happened, try to communicate with people who are watching the movement of a star. The more of these ideas come out, then it's a pretty clever way to attempt to narrow down that search for other civilizations. FE. Do you think the human brain is capable of solving the mysteries of space, or will it be AI, AGI that will help us do that? I mean, we're at a really funny time in history, which is that we are here before the artificial general intelligence was developed, if ever. So, like, one possibility is artificial general intelligence is never developed, and the current state of large language models and transformers stall out, and then there's decreasing returns, and everybody realizes that it's a bubble and it never worked, and we just go back to the systems that we used in the past. I don't think that's likely. I think that clearly there's value to be discovered. And with the current state of large language models and transformers and artificial intelligence, like, we're going to continue making incremental gains at the very least as we move forward. Maybe we'll never develop artificial general intelligence, but even with the current state of AI, we're going to gain value. But people are finding a lot of really clever ways to use artificial intelligence, machine learning algorithms in science. And so things like being able to model all of the chemical interactions that could potentially happen with drugs to find, say, some sort of new antibacterial medicine, or people have been able to test out different kinds of materials. They know the chemical sort of constraints of all these different kind of materials. They feed it into a large language model, and then out pops predicted material capabilities for different chemicals that have just never been made. And there's robots that are combining different materials together, following these recipes that a different large language models developed to find out if these chemicals really do match the predictions made by the model. And they're finding, in some cases, absolutely. And so I think that right now, these AIs, when it comes to science, mostly suck. They're mostly not helpful at all. But there is a lot of really interesting technology that are just coming around the corner, like a much larger token limit. So when you think about when you deal with ChatGPT, you can only put in, I don't know, like 100,000 tokens, which is a lot, but it's, quick starts to lose the thread when you're talking, or if you try to feed it a PDF to try and read it. But say Google with their 1.5 version of Gemini has like a 1.5 million token limit and was able to search for needles in the haystack very well. So you could take an entire YouTube video or a document with 1 million words in it and put it into the large language model and ask it to find very specific facts, and it actually pulls those out. And so right now, the problem is that these things hallucinate, but maybe in the future, they're not going to hallucinate. They're going to do a really good job of being able to give accurate facts. And so then you can imagine this process of assisting scientists, speeding things up, that you're going to explain what you're working on, and then it's going to check every single scientific paper that's ever been written by anybody ever, and then bring it back together for you to find out if there's any needles in the haystack across all of human knowledge that will be helpful for what you're working on. So I think that we don't even need artificial general intelligence for it to help accelerate our science, that scientists working with these kinds of helpers are going to produce some amazing results. The trick is to not over rely on them. Like, you see plenty of hilarious examples of people who are getting things like ChatGPT to help write their research documents, and they're getting exposed as idiots because it's just not ready for that kind of work. So could the human brain solve these mysteries? Over time, sure. We are just very slow large language models. But having the assistance of this technology is going to accelerate our ability, and it's going to allow things that used to require brute force now it's going to be able to come up with ways to solve these problems and get us closer to answers than we ever thought before. And it might just be there's a whole realm of science that we've already reached our limits on what we can do from our own intuition or doing experimentation, and having something that can just explore all possible versions almost instantaneously is going to allow us to step forward. So I think it's just like, it's going to be a combination that very smart people are going to use the best technology to advance science, and that will just continue on the way it always has into the future. Fractured Gamer, what do you think about the city lights James Webb found 7 trillion miles away? I follow James Webb news a lot. I mean, I am reporting on James Webb stories a couple of times a week. You know, we talk about it on Space Bites, and of course, we're reporting on Universe Today. And I have not heard a single science paper that says that James Webb has found city lights 7 trillion miles away. And my suspicion is that the video that you saw on YouTube that said that was a lie, was a scam, that there are just an unstoppable, unlimited number of nonsense gibberish that is being produced and uploaded to YouTube all the time. And they are, you know, they typically have Neil deGrasse Tyson crying in his hands. He's like, we were wrong. And he's so sad, or he's sorry that we lied. And then it's James Webb has just seen the outside of the universe and scientists were shocked at what they saw. All this stuff is nonsense, and none of it is real. And if you actually watch the videos, they don't explain it, they don't provide evidence, and they don't provide any sources. They just rattle in circles for about 20 minutes. And this is one of the biggest threats that YouTube has right now today, is that it is not only like allowing this stuff to exist despite people complaining about it, but it is pushing it, is driving it, it is algorithmically encouraging it. And so like when I go onto the YouTube into the creators tab, and if anyone who has a channel, you understand this, you go to the analytics section and then you click on the research link, then YouTube will give you a list of all of the videos that it thinks are relevant to you, similar to your audience, whatever. And whenever I look at that list, it is 100% garbage. Every single one of those videos is just garbage. That someone is just trying to make money. They're just trying to go clickbait, artificial intelligence, and they are taking advantage of the system, and they are reducing people's ability to understand the real stuff that's happening from James Webb. And I'm not the only person that's noticed this. Like Kyle Hill has gone on a just rampage trying to deal with this. The BBC has done news reporting on this, and it is a big, big problem, and it's just getting worse. And like, really, I have two, like, is YouTube unwilling to deal with this problem? Like, they don't care. Like, you know what? Science was fun. Like, having people understand science was cool for a while, but now we're making a lot of money from this stuff. And so who cares, right? We just don't care anymore. So either YouTube is unwilling or they're unable. They're literally incapable of catching this junk and coming up with some kind of solution to deal with this. And recently YouTube rolled out a new thing where they require people who make videos to say whether or not their videos are made with artificial intelligence, but they're looking for people that are trying to misrepresent things. So if I'm going to have like Joe Biden talk about black holes and misrepresent that Joe Biden discovered black holes, then I have to identify it. But if it's all just this mush of little video clips and bits that come from public resources, that you've got an AI narrator, you've got a script that is written by ChatGPT and it's just going in circles talking about stuff about space, and you package it all together and you put a scary clickbait headline on the front, that is totally fine. 100%. You don't need to label that. That does not cross any lines. And this is the most, I think this is an existential risk to YouTube. And we're seeing this in every corner of this website. And if anyone from YouTube is watching this, like I'm sure you watched Kyle Hill's video, and I didn't see any result. I didn't see anything change. And he made a big impact about it. And then the BBC reported it. And yet, if I go to my YouTube research channel, every single one of those videos recommended to me for compelling content that I should feel inspired by is straight up AI nonsense. And so, what do I think about the city lights that James Webb found on 7 trillion miles away? It didn't happen. And the fact that this information is spreading around on YouTube is going to cause a just complete breakdown of people's understanding of what's really going on in the universe, what these telescopes can actually do, and the very nature of science itself. So fix it, YouTube. All right, those are all the questions that we had this week. Thank everyone for asking questions both in the YouTube comments as well as everybody who showed up for the live show. Just a reminder, we do this show live every Monday at 5 p.m. Pacific time. So if you want a much longer show, many more questions, back and forth with me and the audience, definitely come and check out the live show. We'll put a link to the next one. Now, we're going to be off next week because I will be at the eclipse in Texas. So hopefully I will get an eclipse to see and not horrible thunderstorms, but I guess we'll all find out. So we'll see you in 2 weeks. Now, I'm going to talk about another small channel that you should definitely check out. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilara, David Giltonan, Dougie Stewart, Dustin Cable, Jeremy Matter, Jim Burke, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. All right, I have a bit of a different kind of YouTube channel that I'm going to recommend this week. And this is a YouTuber named Stephen Baumann. And Stephen Baumann is a geologist, and he has a geology degree and he works as a geologist. And so a lot of his videos are about geology. And I really like rocks. And I found a lot of his videos really fascinating, but not just, talking about rocks and in his area and so on, but he actually covers some astronomical topics as well. So here's another recommendation for a YouTube channel for you to check out. So once again, if you know of a YouTuber that has less than 10,000 subscribers, but is doing good work in education, in space outreach, science outreach, geology, even biology, please let me know in the YouTube comments. I'll continue to gather these up and I will share them with you each week. We want to try and help the people with smaller number of subscribers get more subscribers, and this is how we do it. All right, we'll see you next week.